first speaker is James Wen Chou on quantum control and high-resolution rotational spectroscopy of a singular molecular ion subject.
It's my great pleasure to be in this workshop and talk about our recent effort on the molecular ion project at N.I.S.T. Boulder. I realize I'm the first talk on molecular ion, so I can put in a bit more introduction material. Because of the long trap lifetime, molecular ions are identified to be good candidates for precision measurement and testing fundamental physics. And there have been various proposals on testing time variation, possible time variation of fundamental constants and, for example, proton to electron mass ratio using diatomic molecules. And you could use simple molecules, simple molecular ions to measure fundamental constants really precisely. And there's been a really impressive result from Eric Cornell's group on hafnium fluoride ion measurement result. It's not quite at the Acme level yet, but they are quickly catching up to constrain the magnitude of electric dipole moment. And the reason why we want to work with molecular ions instead of going through the courageous endeavor many of us have heard yesterday is because trapping charged particle is relatively straightforward. With a linear pole trap, that's what we use. We apply RF voltage on the two rods that's diagonal and just ground the other two rods. And that oscillating electric quadrupole potential confines the charged particle in the center of this linear configuration. And then just by applying positive voltage on the, we call end caps and electrodes, we apply axial confinement. And that allows us to trap positively charged particles. And to cool them, since we have a toolbox that's developed in laser cooling and trapping of, atomic ions, we can exploit the Coulomb interaction between charged particles and put molecular ions and atomic ions in the same trap and laser cool the atomic ions, and through this, what we call sympathetic cooling, the translational motion of the molecular ions are also cooled. Okay. So trapping and cooling, it's really challenging for neutral molecules, and for us, we are kind of cheating. We are using charged molecules, and that's really easy. So identifying that at our group, we want to develop a general protocol for spectroscopy of molecular ions. In particular, we have been enjoying really high precision in terms of measurement precision and quantum state control for atomic ions. We would like to extend that to many species of molecular ions. The molecular ion we start with is just a simple hydride, calcium hydride. The reason we work with that is because we have lasers for calcium atomic ion. And to get hydrides, relatively straightforward. You just trap two calcium ions, and we leak in hydrogen. Leaking hydrogen into our ultra-high vacuum apparatus. And after some time, one of the calcium will react with hydrogen and get calcium hydride, and then we just close the valve to stop the reaction process. With the toolbox provided by atomic ion quantum control, we are able to cool the shared harmonic motion between the ions in the same trap to the quantum mechanical ground state, and motion of the ions needs to be treated as quantized harmonic oscillator, and we can get to the ground state, and we can also coherently drive to the first excited state, and the atomic ion allows us to do that and efficiently detect the motionless state. For this crowd, I don't need to say what this is, but you just need to know, and the room temperature apparatus, our calcium hydride ion is in the electronic ground state, and vibrationally it's not excited, it's also in the ground state. The rotational constant for calcium hydride is about 140 gigahertz. So at room temperature, it's actually in thermal equilibrium with the blackbody radiation. It's a polar molecule. And nuclear spin of the proton increase the number of states we need to worry about. So at room temperature, only like 1% of population can be found in each of these sublevels. And that's the problem we are facing in terms of doing quantum state control of this of molecules, actually. In the following, I'm going to use this J-1 rotational quantum number J-1 manifold as an example to tell you how we tackle this problem. The levels are actually described by a simple Hamiltonian, and it has exact solution. It's by Rabi formula. At finite magnetic field, we apply about 3.6 Gauss of magnetic field. The levels are in this kind of arrangement. And in each rotational manifold, we identify a transition that, in this case, J-1, we have around 10 kilohertz transition frequency. That's unique in this atomic ion, molecular ion combination. And for J-2, we have a similar situation. This transition is around 13 kilohertz. So with this, if we try to address a 13 kilohertz transition, we know only this transition is being addressed. That's how we can say we are only dealing with two-level system in this case. The way we do state preparation is actually a projective state preparation. We first prepare the motional state shared by the atomic ion, molecular ion in the motional ground state. And then we address this transition that has unique frequency, but not directly on the transition, but the sideband, motional sideband of the transition. So if the molecule starts in this state, the motional sideband would move the population over. And as I mentioned, that our atomic ion provides a really versatile tool set, and we can make a projective measurement on the motional state. And although the probability is small, but we do see that with high confidence, if this motional state was changed from the ground state to the first excited state. And then with that positive measurement, we know that the molecule is definitely in the final state of this driven transition. And since we are only driving this transition due to the signature transition frequency, we know the molecule is in this state. And borrowing from the original quantum logic spectroscopy proposal, we are able to devise optical pumping to concentrate population of the molecule to further increase the signal-to-noise ratio, because we are still facing this 1% population that's like 1% in the signal. So what we do is we drive a sideband, but that moves the population and the shelves the population over. But instead of doing a projective measurement, we cool the motion. That introduces a dissipation that renders this coherent sideband operation irreversible. So that's the dissipation we are adding into the system. So it's pretty difficult to do, or it's not common. You can just apply, introduce dissipation without worry about the population being lost. But for us, this population operation is done coherently, and the dissipation is done through atomic ion. Okay, and we can just keep doing this kind of operation and move population around and concentrate population of the molecule to a target state we like. The way we drive the molecular transition is through a stimulated Raman transition. We for population operation within a rotational manifold, we use a pair of Raman beams derived from 1051 nanometer fiber laser. And to drive sideband transition, we just use a pi polarized and one sigma polarized Raman beam and tune the laser frequency so they just resonantly drive a sideband transition. As I mentioned, this is a coherent process, so we don't excite the excited state of the molecule, so we don't lose the population of the molecule to other unwanted states. And since we only need this laser to be off-resonant to molecular transitions, this laser can be applicable to many molecular ion species. And this protocol could be applicable to many molecular ion species. And I have some animation to further give you some idea of how we do this state preparation. The system started with the atomic ion, molecular ion in harmonic motion, and then the molecule, we just don't know which rotational state it is in. We start the protocol by doing sideband cooling on the atomic ion, and the translational motion is in the motional ground state. And we just don't know which rotational state the molecule is in. And we can do optical pumping to try to kind of align the molecular rotation, but at this point we still don't know which speed it's rotating. And then we start our projection attempts. We would try to address those sidebands of the transitions with signature transition frequencies. We'll try one frequency and see if we succeeded in driving the sideband. And the state detection on the atomic ion would say, no, you didn't hit the right frequency. Okay, so we will try another frequency. Did we hit it yet? No. No, we keep trying until we hit a frequency that excites the sideband. And then the state detection on the atomic ion will say, hey, you succeeded. And now that we would know which state the molecule is in, then that finished our state preparation step. It's ready for further manipulation or a spectroscopy experiment. And if all the effort failed, then we wait for background blackbody radiation to thermalize the population of the molecular ion and start over. And with the prepared pure state, we can do coherent spectroscopy, and this is just our first stage of effort. We were able to get really narrow transition spectroscopy, and for these are the transitions with the signature frequencies. And you might notice that the contrast isn't that great, and this is not acceptable in our group, I would say. Yeah, because they were looking at like 3 nines, 4 nines of fidelity. So the first question is, what's limiting it? And we know that there's some heating that we need to address, and we were able to increase the sideband contrast quite significantly. It's still not 3 nines, but this is really good enough, and it was able to proceed with this high sideband contrast. And we can also coherently flop between two levels with high contrast. So that's really a building block for our protocol. We have pure state preparation. We have kind of high fidelity operation, coherent operation. But you might notice that up to now I have only talked about operation within a rotational manifold, and those are 10 kilohertz, 20 kilohertz transition. And we are still at the mercy of blackbody radiation in terms of getting the molecule in the state we want. So Didi, among others, has a nice proposal that suggests using a frequency comb to drive many different rotational transitions, and all at once, just with one frequency comb directly. And the idea is pretty simple. In frequency domain, the frequency comb can be considered as a mini narrow line with lasers equally spaced by the repetition rate of the pulse. And if we can tune the spacing of these combs properly, we can get one comb pair, comb teeth pair, to satisfy this resonance condition that, for the transition we want to drive. And since these lasers are equally spaced in frequency, the other pairs would also be resonant. So then the whole spectrum can be used to drive a Raman transition. And this has been demonstrated in ytterbium ion hyperfine transition that's 12 gigahertz in frequency, and also to extend it to terahertz transition, it has been demonstrated in calcium ion fine structure transition. And in the lab, what we use is a femtosecond sapphire laser frequency comb, and we split it into two and shift the frequency with two AOMs. And we have a delay line to make sure the pulses would arrive at the ions at the same time. And the reason why we do this instead of tweaking the repetition rate is because for a Raman transition frequency that we want to address, we can decompose it into integer multiple of repetition rate, and then the remainder, whatever the repetition rate cannot cover, we can cover it with the AOM frequency. So you can see that by changing the AOM frequency within microsecond, we can change the Raman frequency we address. And again, all the comb teeth would contribute to driving that transition. And of course, we use that comb to do spectroscopy, and we first prepare the molecular state, as I mentioned in the previous part of the talk. And then we sending a comb pulse that drives the Raman transition and change the population, and then we try to detect the population in the initial state, and we can also detect the population in the final state. And the spectra is, as expected, if we prepare in J-group 2 and for this Raman transition in linear molecule, the rotational quantum number needs to change by 2. So we see that we remove population from J-group 2 and it shows up in J-group 4. And we reversely, we can prepare in J-group 4 and we see that the population shows up in J-group 2. And since we can prepare the state and we can detect the final state, that facilitates our assignment of this observed line to a specific transition. And we did these kind of rotational spectroscopy on many transitions. And we were able to get like sub-100 hertz statistical uncertainty. And with these many transition frequencies, we can try to derive the rotational constants to sub-kilohertz, centrifugal correction, second centrifugal correction, and you can imagine we can get many terms in terms of this molecular constants. But there is a bit complication in here, and you can see everything seems to work pretty nicely. But just recently we realized the systematic shift needs to be really well taken care of. What we had observed is there is some problem in our setup, in that when we are doing this spectroscopy of this transition, we prepare the state here, try to drive that transition. This is now like below 10 kilohertz, and we try to detect whether we made that transition by looking at the population here. And what we have seen was we saw 2 dips. That means there are 2 transitions. But the selection rule for this pi polarized light, sigma minus polarized light, actually only allows 1 transition around this this region, this frequency domain. So we were scratching our head, what's going on? And then eventually, when we try to change micromotion, that's the electric field of the trapped RF, that's providing the confinement, that's also driving a small motion of the ion. And when we changed that, we saw that the splitting reduced, and that prompt us to develop a model, and I don't know if this is correct, but this is the current working theory, that we are looking at a Raman type of coupling from the trapped RF electric field that's basically 0 Raman frequency. That's why we don't see that when we do spectroscopy on these transitions, because they are not degenerate, but these levels, they are near degenerate, and we are basically dressing the states that's near degenerate, and then this splitting is basically the Rabi ray of this dressing. And since the trapped RF electric field might have other polarization, we have dressing for other states. And with the cone pulse, we can also do coherent manipulation between rotational levels, and we can see that we have nice Rabi flop between different rotational levels. And we have also started exploring the quantum information type of operation on molecules, on molecular ions. In particular, we have studied entanglement between calcium hydride ion and atomic ion. What we did was using 2 levels in calcium ion, one in S manifold and the others in D manifold. And for the molecular ion, we can choose 2 levels in the same rotational manifold to start with. And we initialize the molecule, atom motion each in a pure state. And then what we did was pi over 2 molecule motion sideband, just moving halfway of the population, half of the population away from the initial state. And then we get the equal superposition of either the molecule is spin up or spin down, and the motion is in the ground state or first excited state. So this is actually an entangled state of the molecule and the motion. And then we just map the state of the motion onto the atomic ion with a pi pulse. So for us, it's been done for a long time. So at the end, we have spin up and S state plus spin down D state equals superposition. And that's a quantum entangled state. And to verify the entanglement, we did measure the population of the state, and also parity flop. The fidelity is derived from this fringe contrast to be around 87% fidelity. It's still not nice, but I mean, not above 90% or too nice, but it's still a good starting point. And with the molecule, the reason why we want to do this is the two-level system in the molecule could be in different rotational state. So they could be the spin down, spin up state could be separated by 855 gigahertz. And we are able to create an entangled state with a bit, somewhat lower fidelity. But this is proof that molecule could be subjected to quantum information type of operation, and the molecules could provide a broad selection of transition frequencies that if we want to talk to other platform with, say, optical qubit or superconducting qubit, the molecule could provide a selection of transition frequencies. Okay, to summarize, we have demonstrated probabilistic projective molecular state preparation with Raman beams, and we are able to coherently manipulate molecular states with either CW or pulsed Raman beams. And terahertz rotational transitions were measured precisely, and you can infer molecular constants. And we are using far-detuned Raman beams to coherently manipulate molecular state. So this is, we think, is applicable to other molecular species. And we have demonstrated atom-molecule entanglement. And here's an experimental setup. We compared to what I heard before, in this meeting, I think it's relatively simple. We have ion trap and Raman beams coming in, these two ports, and laser light going into the for addressing atomic ions. Here's the group. Didi and I started the experiment, and Dave Libran also provided significant support. And many other postdocs and Ihan especially contributed to the entanglement experiment. Okay, thank you for your attention. Thanks.
Can you say a little more about this RF trap Raman?
Yeah.
It's drawn on a rotational transition.
Yeah. So.
Which is how far away?
No. So you see, this is electric field oscillating at the trap RF frequency, and you could have pi polarized electric field.
I guess, but the J plus 2 state is like really far away.
Yes. It's like.
You're near the center of the trap, so I think like the 2 photon Rabi frequency is like even smaller than that, but it's not.
No, it's not. Because we have axial RF field that's not zero, and we estimate it to be like a kilohertz. In this case, it's kilovolt per meter. Yeah, but you see over here it's like a couple hundred hertz. Yeah, but we haven't got a quantitative agreement yet. But I think we will need to treat this coupling as one term in the Hamiltonian, not as a perturbation. So we haven't done that yet.
Yeah, so maybe I missed it, but did you say what the coherence time is when you create rotation state superpositions?
I did not mention that, but I think that's next. So, well, this is Rabi oscillation, but this kind of Rabi oscillation gives us like good contrast until like 5 milliseconds. But it's not saying a T2 is 5 milliseconds, but it's the right ballpark.
A related question, what limits that time and what limits your 500 hertz line width? And also, how long does it take you to get one of those narrow spectra?
Okay, so first, what's limiting the coherence time? It's because we didn't go all the way to stabilize with optical reference. because we want to tell people this is not that difficult. So what we did was just referencing the repetition rate to RF synthesizer. So it's the limit, it's the line width of the, or coherence of the synthesizer thing. And we do have plan to just use one of our many clock lasers to just stabilize the hell out of it. And the other question is, how long does it take? So you see, right now our state preparation is still probabilistic. So we are actually doing like many of these spectrum in one experiment run. So within an hour, we can get 4 or 6 of the spectrum, because we don't get to choose where the molecule is, but we do know when the molecule visits the state. So we get 6 spectrum in, say, an hour. Yeah.
I'm just curious. You mentioned in the beginning of your talk that techniques you developed is good for any other.
Not any other, but yeah.
So, but from my experience in this field, I understand that hydrogenic ions are very special.
It is. Oh,
Yes,
okay.
they have very nice rotational structures when it's not true for more heavy ions.
Okay.
Would it be okay? Would you do that?
Yeah, you see, the heavier ion would have lower rotational constant. But our state preparation did not rely on the rotational constant. Yeah. So what we rely on is some transition with unique transition frequencies. So I think for, say, so for molecules, I think the rotational transitions would be unique in frequency because they are not equally spaced. So that's one thought, that if we can't identify this kind of hyperfine transition with unique frequencies, we could use the comb to drive sideband of the rotational transition. But there are other tricks we can play.
I think you said at some points in your experiment you have to wait for the ion to rethermalize with the black body. How long is that?
It's up to 10 seconds, I think. Yeah, but the lifetime in say the ground rotational level is like 6 seconds at room temperature. Yeah.
All right. Any more questions at this point? If not, then thanks, speaker again.